capture a few things. Oh, sure. Make sure it turns on. All right, guys, let's take a look here. What's the claim that's being made? Now, where do you see greater or equal to?
I'm not sure, I guess. It's percentage, right?
Yeah, it's a P. That's true. This is a percentage problem, so you're going to use P's, not mu's. But it says, does the evidence support the claim for Kentucky?
Equals 0.5.
Yeah. So it is 51.7%. That's the claim, right? So the claim would be P equals 0.517. So where's that going to go? So what's the high going to be? So we're going to have a one or a two-tail test? Two-tail test. And what do I mean by check NP and NQ? Check them for what? Yeah. So do NP times NQ and figure out. So we get NP would be 221 times 0.517, 11. And NQ would be 221 times point.
4,830.
I like it. Now, if you stop and you calculate p hat, you don't calculate p hat until you get to step 4. That's where the sample first comes in, right? This is p. This is not p hat. So it's got to be the thing we're assuming to be true. That p right there. And you get whatever the hell. 117. What is it, 114 something? 140 blah, blah, blah. 106 blah, blah, blah. Those are both definitely bigger than 5. Check. So what does that mean? Normal enough, so then I can use z-scores. I like it. Z-scores, woohoo! So alpha's 0.05, told us in there. Two-tail test, we figured that out. Z-scores we can use, we figured that out. Right? I could be really mean right now and say, when do you use t-scores for a NPQ problem, but it's never. Either it's normal enough and you use z-scores, or it isn't normal enough and you don't do shit. I like it. Now it's two-tail test. Alpha's 0.05. So you look at two-tail, the second row, find 0.05, and just go all the way down to get a z-score if you're using the t-score chart, right? Yeah, what do you get? 1 point. Yeah, 1.96. Yeah, so two things. It's not a t-score problem, right? It's a z-score problem. If you use the t-score chart and you don't want a t-score, you don't stop. If you stop, you get a t-score. If you go all the way to the bottom, you get a z-score. Why does that make sense? Because t-scores were invented for when we don't know sigma, but when our sample gets really freaking big, S is basically sigma. That's why the t-scores are allowed to become z-scores. I don't require them anymore to be bigger. Two tails, right? Two tails? So somebody help me out. What confidence interval is this related to? 95%. 95% confidence interval, 1.96. 90% would be 1.645. Right? So there's my rejection region. This is what far enough away is. So what happens if I get in there? So if Z star is less than negative 1.96 or greater than positive 1.96, that means I'm in there, I'm in the rejection region, and it's called that because if I get in there, I can reject the null. Support high. So you have got to transition into why does what we're doing make sense? And I know some of you guys are going to be like, that makes sense. But if you just stop and think, I've tried to get you to a point where you can kind of reason why this stuff makes sense. The first couple steps really are just window dressing almost, but I've got to know what the hell I'm talking about. Because this feeds into this. And then secondly, I've got to know what I can use. Can I use anything, or do I have to use a t-score sometime? Oh shit, so I got to know which thing to use. Once I know those two things, I can then do step 3, which is establishing what far enough away is. It used to always be 2, right? When did the min and max usual, when did it happen? 2 steps away. But now we're being a little more specific. Now step 4 is, now that I know what far away enough is for a sample to show evidence, I go see what my sample did. How far away did it end up? So what's p hat going to be? 520? I like it. And you can go at least 3. So if you want 4 places, it's even better. But at least 3 places. I know it's still like 5.2, but I like it. So then Z star will be my sample data minus this guy divided by the square root PQ. PQ right there, 517 and 483. Divided by N, which was, it's right in front of you, Jeff. There you go, buddy. 221. So I would throw all this stuff in there. See if this shows up. So I would just go. Where'd it go? There's 0.52 minus 0.517 divided by square root 0.517. That's 0.483 divided by 221. I get that. Is that what you guys got? Like 0.09. Now what is it about that? That's kind of extreme. In what way? What's this all about? This is all about getting really far away from something. How far away did we get? How far away did our sample get? 109, not even 1/10 of a step away. It's not very far at all. Shit. It's like right here. So we didn't make it. We didn't make it. So what can we say right now? We failed. We failed. We didn't make it. We failed to what? Failed to reject the null. Failed to support the high. Which one is the claim? Yeah, the ho is the claim, so you want to use that language. This is the step that a lot of people get tripped up on. They're like, when do you say what? The claim was the ho, so you're going to use that language. We have not found sufficient evidence to reject the claim that, whatever, I've forgotten now. We have not found sufficient evidence to reject the claim that the percentage, remember it's Kentucky, Right, the percentage of
Homes
homes heated by natural gas. Thank you. In Kentucky is 51.7%. So we haven't found evidence to reject this claim. We haven't found evidence that Kentucky is different than the national percentage. There's probably a state that is different enough because they have something else going on.
Do we have to use those like exact words, or can we use something like we failed to reject? Like weird.
The evidence idea is really kind of important. You know what I mean? We haven't found sufficient evidence, but it's sort of implied yet. You know, maybe I could do another study and it would show it. But I'm not really encouraged by my findings here. I mean, that's freaking dead on. Holy shit! It's almost, you know, like I should be like, well, maybe not spend a lot of time looking at that. But if I would have gotten like 1.8 or something, then let me do that study again. I got really close. Maybe. Okay. So again, we've been doing, and I know you've been living through this, so you know this. We've been doing a lot of hypotheses. The steps never change, right? So here's the first example of a slight change, not in the steps, but in the way we do the steps. So I don't just check N here. I've got to check NP and NQ. I don't use X bar minus mu, because I don't have X bar and mu. I use the P stuff. So those are the only two changes, and they're just slight tweaks. They still have the same idea behind them. Okay. Is it normally enough? And how far away did my sample get? That's the idea behind them. Same idea. So what we're going to get into today, is more hypothesis tests. And this is the one that's actually the one that we're more used to be honest. And again, this happens a lot, trust me, because there's you could have a known average lifespan of dolphins, like going back, and then you're worried about a small area. You're like, are they different? There was like a spill of something, and you're like, I'm worried that it's going to affect them there. You with me? So you take a sample, and so you know the mean. And you're just testing the claim that their mean is less. Do you guys see what I'm saying? Like they were affected by the spill of this toxic whatever, right? Or now they're all superhero dolphins. I don't know, right? But we're going to check to see if their lifespan was affected by this. So it makes sense then that we actually know mu. But like we said before, when we're doing confidence intervals, we're like, well, no, normally we don't know mu. Normally we don't know sigma, right? So chapter 10 is all about comparing two populations, taking two samples and comparing them. So this we're used to this. If I want to test a drug, what do? I have a group of people volunteer. Once the FDA says I can use human trials, and I separate them into normally 3 groups, to be honest, right? Let's just say 2 groups right now. One group is going to get the real drug, and the other group is going to get sugar pill. I like it, placebo. Right, and then we just check to see if there's a significant difference between, because there is, of course, the placebo effect. People like the game managers must do something, and your brain makes something happen. It's kind of nifty, right? But then if the real drug has a better effect than that, then that's evidence, or better enough, that's evidence that the drug works. So then, yeah. But I'm taking 2 samples from 2 different populations. The population of people that would take the real drug and the population of people that wouldn't. To take something different. Now, why would we have a third group? What would the third group be? What do you think?
Double blind.
Double blind just means that nobody knows who's in which group. The third group would get nothing. And that's just comparing to see how big the placebo effect is in this case, right? Because it could be different based on what's going on. Okay, because maybe sugar is actually here something new, right? So it's not just the sugar, but it's like, that's the drug. He said, yeah, it helps. Okay, that would be neat. Oh shit, if they said sugar cured something, I would be so happy. Okay. So let's talk about how things change if I now want to deal with two samples. All right, cool. So we have two populations. So it could be anything. It could be people getting a drug, people getting a placebo. Dogs that live in the city, dogs that live in the country. Men, women, people over 50, people under 50. I mean, any way you can break things up into groups, that's what the populations could be. From each population, so each population, like we said earlier, they actually have a real mean. Let's start with the means. Mu exists for each one. This is mu1, mu2. That's amazing. We're going to take a sample from each one. And let's start off with, well, it doesn't really matter, Jeff, so let's just do it the way it normally happens. And of course, if we take a sample, you find a sample mean. We can also find a sample standard deviation. I like it. So what happens to the z-score formula? Well, hopefully you guys understand. The one sample formula from chapter 9. So remember what that looked like. Let's say T star here, Jeff. Yeah. It's just this. It's just a good old bam. Right? Let's put an S in there for. I'm dealing with samples here. Let's just make this an S. There you go. I like it. Where S sub x bar was what? That was the. So we have to adjust the standard deviation. So you take the old standard deviation. Divided by square root of n. Right? Is that cool? That's what are we doing? That's what we did before. That was step 4 in the hypothesis test. Calculate the test statistic. I like it. So now, chapter 10, I'm not just going to have one sample. I'm going to have two. Everything is going to double. Okay, so I'm going to have x bar 1 minus mu 1 plus, plus. Let me say it like this. X bar 1 minus x bar 2 minus mu 1 minus mu 2 all over. Now we got to talk about what happens down here. Oh, let me do this. There we go. That's better. So see how everything just kind of doubled? Pop. Pop. Why did everything double? Because I've got two populations. I've got two samples I'm dealing with. Love you guys. So let's really look at this sucker. Let's analyze the stuff out of this thing. So normally that's what that is, but now I'm going to double everything. So what's that going to now? Let me see if you guys can take this step with me. I want to put everything under the square root so I can just attack it more directly. Right now I got one thing under square root and one thing not. So how do I make everything go under the square root? Why can't I kind of put these together? Because s is not in the square root. So what is s? S equal to the square root of what? What's s equal to the square root of? That's what do it. What do I take the square root of to get s? S squared, right? Now I can make one big s, square root of s squared over n, like that. So everything's in there. So what does that become now? Yeah. So now this is going to be step 4's Z star. Now, to address something a little weird in the formula, some of you guys are like, well, the whole formula is weird, so it might take you a while, but hopefully you guys see how it's the same formula, just everything's doubled. I have to have 2 of everything because I have 2 different samples, 2 different populations. Normally, our null is going to be mu1 equal to mu2 or some kind of equality there. Now, if mu1 equals mu2, and think about it, what are you trying to show evidence for if you think you've made a drug that is different from the old drug? You're trying to show evidence that it isn't equal to something, that is, right? Okay. So normally the null is that these 2 are equal in some way. So if these 2 are equal, what is mu1 minus mu2? 0. So for us, this is going to be the formula. And I kind of like this formulation because what is it that's going to show me evidence? Like if I took all the women in here and took all the men, and we did confidence intervals for grades in here before, I think, and I did a hypothesis test and I thought, test the claim that the mean grade in here is equal, right? What would show evidence that they weren't equal is if the sample means were really far apart, really different, right? So the difference between the sample means, the bigger that is, the bigger that this is, that means the further away I am from the middle being that they are equal. So I like that this kind of focuses on the difference between the sample means has got to be big enough to say that the population means are different. I like it. So let's try an example. Let's try a problem out. It's going to be the same good old 5 steps. Right? Well, this 5-step program. Let's see. Oh yeah, let me leave this up here. I like it. So let's say that this is, let's just do that. Let's just do that. Population 1 is women. Population 2 is men. And this is the grades in some class. So let's say that we don't know what this is. But we take a sample. Let's say we take a sample of, put a little n here at the bottom. Let's say the sample size of the women is 48. And for the men, it's, what do you got, Jeff? Let's say 61. I like it. Now let's say that for these guys I get, it doesn't matter. Let's say we get 79.42, and for the dudes I get 76.19. Everybody with me so far? Okay, so this is the population of women, this is the population of men. Took a sample of that size from each, looking at their average grade so far in statistics. Let's say the standard deviation here is 13.07, and over here, let's say it is 14.11. Okay. So we got all of our basic stuff. And let's test the claim. Oh, yeah, that's right. It's over there. Let's test the claim that the means are the same. And again, it's funny to me how, just to stop somebody from doing this, we've gone through chapter 9. We've already talked about this many times. But somebody will still say, well, right there, man, they're different. I am done. And of course, why is that not good enough? Why do I have to do those 5 steps? Why can't I just stop and go, yeah, I got eyeballs. They're freaking different, Jeff. The shit. Why do we do all these 5 steps? You just want something to look at. You want something to grade me on. Yeah. Why is that? Why can't I just stop right now and just say, yeah, they're different?
It's just a sample.
It's just sample. I want to say something about the whole population, and I've only got a sample to work with, right? And I'm kind of talking about, I don't know if you heard me, I'm talking about all stats classes right here. So this is a relatively small sample based on how big the population is. So it's definitely not enough information to stop. I need to see, are these different enough to show evidence that all men and women are different. The average of all of them are different. I like it. Okay. So let's see. So the claim is that the means are the same. So here's, there's going to be some differences in a few of the steps. Obviously, I've got 2 samples now. Something's going to change. Let me take this away. Everybody's got that written down somewhere, hopefully. This is the T-star formula. And now I'm going to take it away. Ha-ha. The claim is that the means are the same. So, of course, now see, here's the main difference. There's no number. The claim is about 2 population means, neither of which I know anything about. So I'm not going to have any numbers that show up in my hypotheses. It's going to be a relationship between 2 population means or 2 population percentages. I can't say it's greater than 17 because I don't know if one of them is 17. I don't know. It's just the relationship between 2 unknowns. So I'm going to have unknowns everywhere here, right? Now, but still, which one is that going to be? The whole. Because it's got an equal sign in it. So what's the high going to be? Not equal. So how many tail tests with this thing? 2. Yeah. Now what's interesting here is there are 2 samples, right? Some people seem to think that they have to be the same size, but hopefully you understand that doesn't matter worth anything. Does anybody have trouble with that? They don't have to be the same size, right? Did this have to be 48 even in the first place? Would you go, if I put 49, you're like, wait a minute, what the shit? So of course, each sample doesn't have to be a certain size. They have to be equal to each other. Now, in order to say that I can do something in this case, because I didn't say anything about the populations, because I don't know anything about the populations, what do I need to say on the second step? It's the only thing that matters about the sample sizes. Both sample sizes are bigger than 30. I like it. So N1, let me put N1, N2. N1 and N2, bigger than 30. So that means I can do something. Now what can I use to do that something? I'm trying to remember which way they do something certain. Ooh, that's right, they do some weird shit. Ugh. What can I use in this case? What's the other thing I have to figure out? So that just tells me that it's normal enough. Yeah, which standard deviations do we know? Sample standard deviation, so I have to use t-score. T-scores, I like that. So I got to use t-scores to do this. Yes, ma'am.
I was just wondering if this is the Untitled Chapter 10 problem that we're going to do today, or if we're doing more examples.
It kind of depends on how long this goes. So we'll find out. I'm considering options right now. So what do you think's gonna what do you think I have to worry about for the next step? What is the next step? What is the next step? What's the next step after 2 to figure out what I can use? Rejection region, right? The figuring out what far enough away is. I think the book calls it critical region, but I call it rejection. So let's say use alpha equal to point, what was it? Yeah, 0.02. Now, what's the trouble with this? How do you figure out what t-score to use? And you only want to use a single t-score idea, right? How do you want to figure that out? What's the problem? No, the sample's plenty good, right? Samples are over 30. But the problem is there are 2 samples, right? So I don't want to use, this is what I was trying to remember, the book uses this horrendous formula to figure out degrees of freedom, which is so unnecessary. Let's see if I even want to show it to you. Blah, 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 blah. Where is it? There it is. Oh my God. It's disgusting. It's gross. I'm not going to use it. What I want to use, I'm trying to remember if they use something like that I want to use somewhere. No. I don't want to use that. Yeah, okay, I can do that. I was just trying to remember which one I want to use. We're going to use, for this, we're going to use degrees of freedom is n1 plus n2 minus 2. And this sort of, if you think about it, it makes sense to some degree, because if I have a single sample, it's going to be n minus 1. So now with 2 samples, you add them to get sort of a feel for your whole sample in a way, all the people you're dealing with or whatever it is. Minus 2, because minus 1 for each one. And this is a rough approximation of the really disgusting formula they use in the book. So in this case, what would our degrees of freedom be? Yeah, 109, right? 48 plus 61 minus 2. 109 minus 2 is 107. Now, of course, you got this crazy-ass instructor that doesn't let you use technology much. Too damn bad. We got that T-score chart that goes from 100 to 200. So what are you going to use? 100, hell yeah, right? So we're going to use 100. So take a minute and see if you can figure out what the T-score is. It's 0.02, two-tail test. Degrees of freedom is 100. I don't even know if I brought my... I have to go off of what you guys say. I trust you guys. So I got 1 vote. Got 2 votes in. I like it. 3 votes in. I like it. Everybody else is like, just that, Jeff. Just stop it. All right. So negative 2.364, positive 2.364. 0.02, two-tail test. Stop at 100. I like it. So if I wanted to state this in words, when do I reject it? If my T-star is, just like the last one we did, less than this or greater than positive that, you can reject the null, support the high. So once you realize what's happening here, this is sort of the middle here is like there is 0 difference between the two. That's the middle. The middle is saying there is 0 difference. And I just want to find a big enough difference between the two, big enough relative difference between the two to say that, yeah, it looks like this is good evidence that both populations' averages are different, not just the samples. They have to be quite different. So now step 4 is going to be using that huge thing. So let me let you guys just attack it. Here's the formula again. N, yeah, there's N1, there's N2. Sorry. Oh yeah, because mu1 equals mu2 is the, in fact, this will always have some kind of equal sign, so that will always be 0 for us. For right now. I love the always for right now. That's a good job. Gotta remember today to show you this. All right. So considering I made all this up, you think I know how this is going to come out? I have no idea. So this one's really, really got to be careful about, putting this in the calculator. Again, if you have the newer one, you don't have to worry about parentheses because your root symbol just grows. It's kind of nice. So x bar 1, 79.42, minus x bar 2, 76.19, divided by square root 13.07. The biggest mistake is the same mistake that we make in a lot of different areas, is forgetting the poor little square dude. Divided by 48. Another mistake is like mixing up the s's and the n's. S2, N2, S1, N1, they got to go together. 14.11 squared divided by 61. So what do you guys get for that? Ooh, it's lifted. Anybody else get anything yet? What did you guys? Anybody got something? Or is it just me? You got something, you just don't want to say. I'll start it off. It's 1. That made you feel better. I like it. 1.24 roughly. I love it. I could see in your eyes. You're like, got a number. I ain't gonna say that shit. I'm always saying that. It's supposed to be 10 or something. Forget that. I don't blame you. 1.24. So what does that mean? Yeah, we failed. We only made it 1.24 steps, not far enough away. So we fail to do both things, right? We fail to, we can say right here, fail to reject the hope, fail to support the high. Which one was the claim? I think I erased the claim, but hopefully you guys have the claim. Oh, there it is. The hope. So I want to use this language, the reject language. Do you guys see that step? That's the step where people just kind of guess and pray, Pick a word, throw it in there. But it's just totally that. The ho was the claim. That's the phrase I use. Fail. So we have not found sufficient evidence to reject the claim that the mean grades of men and women are the same. We have not found evidence to say that they're not the same. I love that. Math goes double negatives all day freaking long. We have not found sufficient evidence to reject the claim that the mean grades of men and women are the same. Now, careful, this is not proving they're the same, but this is saying it's not sufficient evidence to say they're not the same. I do want to show you something. Let me see. Every day for the last several classes, I've discovered a study that I wanted to show you, and then I decided to let us out of here before I showed you. So today I managed to catch myself. I just always like to show you how real life application is mirroring what we're doing in here. So this is beautiful. This is perfect. This is sheep face recognition by sheep. I love it. And who the hell's sitting around going, you know what we should study next? Look at that sheep over there, knows who I am. I'll let you guys go with that. Let's see. I love this. They talk about materials and methods. They talk about procedures they use. They talk about blah, 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 what facial recognition is. Here's the results. Now wait, right up here, where is it? Where'd you go? There. The threshold for statistical significance was set at p less than or equal to 0.05. The most commonly used significance level. Are you guys with me? A couple things to realize there. 0.05. And the freaking language is the same. Of course it is. There's a reason for this class. And we do this kind of shit we're doing in the real world. Holy shit. So here, real quick, I'm not going to get into all the... We found no difference between the selection performance on the different faces, whatever that means. You can read this whole thing. But look, p equal to 0.1. 0.1. Is that relatively big or relatively small? 0.1 is what percent? 10%. That's big. That's huge. That's why we said we found no differences. Now, see how they state it like it's fact, but they immediately follow it up with the evidence. Right? So that's normally how you do it, and you just know that it's not fact. It's just that they didn't show evidence that there was a difference. So that's why we found no differences. We have not found sufficient evidence to blah, blah, blah. Right? Like that. But a highly significant improvement across sessions. I guess they trained the sheep to recognize faces. I guess now I want to read this thing. But p less than 0.001. That is very significant, right? In which the sheep improved. And then look here. What is this? What kind of thing is that?
Error.
Holy crap! Well, I didn't want to do that. I did it. It's too bad. That thing that I had up here, that's a confidence interval, right? 3.84 plus or minus 0.48. That's a confidence interval. I love that shit. P equal 0.71. That's pathetic. Do you see what I'm saying? You can actually read a journal article where they do statistical analysis, and you could probably right now actually make sense of their results. Not just read the ABC News whatever shit report that doesn't tell you any specifics, and it just goes, eggs will kill you! And then you go, well, no, ABC News, that's not really what came out of there. It gets people to click on your shit, but don't be doing that. Anyway, so that's what you should always do. Now you're better capable of checking out the real story instead of the news-grabbing headline. Okay. Ooh. And this we might get into a little bit of later this semester. Good old ANOVA, analysis of variance. Oh, yeah, that sounds painful. Okay. There were some other ones that I kind of decided not to look at. You gotta love when they mix the onion. 90% of bike accidents preventable by buying a car. That's the onion, though. You guys know the onion? Yeah, anybody? They publish news that sounds like it could be fake, and nowadays it's like, is everything the freaking onion? I don't know. All right. Did I give you guys, let me do this while I'm thinking about it. I'm going to give you the practice test. I did? Really? Oh, that's right. There's so many people not here. Anybody else need one? Yeah, extra one.
Well, can I do my question?
Can you do who?
Do you want my question?
Yes. Need one?
We're just hoping to get in here.
point out on the practice test, number 3 is a confidence interval problem. But on number 6, I say for problem 3, perform a hypothesis test. So that's going to be using this stuff here. So number 6 goes back to number 3 and it says, perform a hypothesis test on this. Everybody with me? I like it. Let's see, blah, 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 blah. Okay. All right, what else did I want to do in chapter 10 without driving you guys crazy or more crazy? Oh, it's not that really. It's just the fact that the square root of s squared over n is s divided by square root n. They're the same thing. But we suck it all into a square root so I can double it easier.
Right.
Yeah. Now there's hopefully you understand. There's a lot more math behind this that's at a level that most of us don't know enough about to go into. I mean, why is it plus? You know, I kind of glossed over it, but there is 2 standard deviations and 2 sample means. But why is it plus, Jeff? Well, we can't talk about that. I mean, it's a little bit more advanced, but it is nice the idea that everything's doubled. You can see that happening. Somebody had a hand up. Okay. I do want to say a few things about section 10.2 is the same stuff, but with standard deviations that are known, in which case, like population standard deviations are known. In which case, what's the difference? You can then use z-scores. It's amazing. So it's the same stuff. Same formula. Let me think. Somebody have that homework sheet? I've given all mine away. Somebody have the homework sheet. Which section's in 10? I think it's 10, 1, 2, and 3, isn't it? 1 and 2? Okay. I like it. So I already 3 out. That's funny. I like it. So that's it. That's all I needed to say. Are you guys okay? We end now? I think you probably are. All right, so on Wednesday I'll have the answer key for this. Yeah.
What'd you say about 3? I put a star, but I didn't listen what you said.
Oh, 3 asks you to make confidence intervals, but number 6 tells you to use 3 to make do a hypothesis test.
Okay.
So that's just like this.
Okay.
The 2 samples, yeah.
Yeah, you said it. I made a star, but I didn't pay attention to anything.
And then you're like later, and you're
I
like,
was
why is this
number
special?
3.
We have quiz on Wednesday.
No, because we have a test next Monday. Yeah.
Do you have time to go over the conferences and
Oh, and the quiz that we used.
Yeah.
Yeah, sure. Yeah. Oh, go ahead.
That's the way to give the last.